Happy Republic Day with peace in my mind, freedom in my soul, and pride in my heart. And I wish you Happy Republic Day. This video I have dedicated to birth anniversary of Swami Vivekananda. The date was 24th January. Welcome back. In my earlier video, I had discussed about maximal ideal and principal ideal. Today, I will discuss this topic elaborately obviously, but at first I will discuss principal ideal domain. You must know about the principal ideal. Principal ideal means the ring which is generated by single element. Here, extra thing is principal ideal domain. An integral domain R is called P.I.D. if every ideal of the ring is principal. That means a principal ideal domain is an integral domain of the ring in which every ideal has of the form, since this ideal is generated by only single element, that means this is obviously this type singleton set A, where this is equal to set of those element Ra such that R belongs to the ring, where for some A in the ring R. For example, consider integer. Obviously, integer be integral domain. We all of us know in integer all ideal is look like in Z types, and which is actually generated by singleton set N. So, obviously, by these rules, we can tell integer be P.I.D. Are you getting the idea? Well, our next example is Gaussian ring, which is look like A plus IB, where AB belongs to integer. Obviously, this ring be integral domain. Now we have to check this ring is P.I.D. thing. How will be the ideal here? One can possible ideal generated by I. This is obviously principal ideal because this is the generated by single element. Other can be AI, where A be any integer. This is also Pi. Other possibility is only I. This is also Pi. And other can be generated by the whole element A plus IB. If you see other ideal, then all ideal will be here generated by only singleton set. So, in Zi, all ideal be principal ideal. That means Zi is example of P.I.D. Similarly, we can tell all field be the, if we consider all field be as K, this is also example of P.I.D. because we all of us know all field be integral domain. That means there exist only two ideal, one zero ideal and other the ring itself. So obviously all field be P.I.D. Similarly, if we consider the polynomial ring Kx, where K is a field, this is also example of P.I.D. Okay? And this proof is very easy proof. Try to yourself. My all viewers have clearly understood what is the principal ideal domain. Now I will see some example which are not P.I.D. First example is polynomial ring Zx. Obviously this ring is integral domain. Then to check the P.I.D, we have to find all ideal in ZX are principal ideal. If we consider ideal generated by 2 and x, which would be look like 2f1x plus x f2x, where f1 f2 belongs to z2x. We cannot write this ideal as a single element. So, for this ideal, ZX is not a principal ideal. Are you getting? Similarly, we can tell kx1, x2, xn is not P.I.D when n greater than equal to 2. Here k is any field, because if we consider n equal to 2, then the ideal x1, x2 is not principal ideal. So, this ring is not P.I.D. We will see some example which had come in CSIR net exam about the P.I.D. First exam come June 2017 net exam. The question is very simple and very easy. Which of the following ring are P.I.D? First QX, second ZX, third Z mod 6 ZX, fourth Z mod 7 ZX. I hope my all viewers have understood what is the P.I.D of this ring. First QX. Obviously QX be field. That means that imply always QX be integral domain. So, this is obviously P.I.D. because every field always be P.I.D. Are you getting the idea? I have told you when K be field, then obviously Kx be field. Second example is ZX, which is not P.I.D, which I have seen few minutes ago. And third, Z mod 6 ZX. For this, consider an element A equal to 2x, which is obviously belongs to this ring, and other element B equal to 3x, this is also belongs to the ring R. Then what would be A dot B? A dot B would be 6x, which is equal to 0 in the ring Z mod 6 ZX. Therefore, notice these elements both non-zero, but their product be 0. That means this ring contain 0 divisor. So, obviously this ring not integral domain. So, this is not P.I.D. And fourth example is obviously Z mod 7 ZX is field. So, obviously this is P.I.D. Are you getting the idea of the P.I.D? I will see similar type of example which had come CSIR net December 2017. The question is, which are following be P.I.D? The first option, ZX modulo x square plus 1. At first see the first option. Here the ring is ZX modulo x square plus 1. And we all of us know by first isomorphism theorem, this is actually isomorphic to Zi. And since I have seen few minutes ago Zi is P.I.D, that means obviously this ring would be P.I.D. Are you getting why I have told you why my previous video is more important to understand the ring theory in better way? Because I have taught in my earlier video ideal of a ring and maximal ideal, prime ideal, ring isomorphism, and I have seen kernel always be ideal of a ring. So we can tell easily this ring is isomorphic to Zi. And second option is Zx. Obviously Zx not P.I.D. And third option CXY. Here notice I have discussed this part few minutes ago. This is also not P.I.D. because here all ideal be generated by f of xy. Our fourth option is Rxy modulo ideal generated by x square plus 1 comma y. We can write easily Rxy as Ryx. We all of us know this is, which is polynomial with variable y whose coefficient be x. And by this Ry, from this expression Ryx modulo ideal generated by x square plus 1 comma y, which obviously will be isomorphic to Rx modulo ideal generated by x square plus 1, which is actually isomorphic to complex number. And since complex number be filled, so obviously this ring is a P.I.D. Means option 1 and option 4 is a right. Now I will see one interesting theorem. Let R be a principal ideal domain and small p be non-zero prime ideal of the ring R, then this ideal P is maximal ideal. That means when a ring be P.I.D., then every non-zero prime ideal always be maximal ideal. Let's see the proof. Since P is principal, then consider P is generated by A. Since here considered P be non-zero prime ideal, so for some A not equal to 0, and this is possible because P is always non-zero. Now we have to prove P is a maximal ideal. That means there exists no proper ideal between P and the ring R. Consider this is not. Consider I be an ideal of the ring R such that P contain I contain R, and since I is principal, then consider I is generated by B. Okay? That means ideal generated by A contain ideal generated by B contain ideal generated by contain the ring R by the assumption. And from this line we can tell easily, obviously small a belongs to ideal generated by B. That imply A equal to BC, for some C belongs to the ring R. Since P is prime ideal, that means A equal to BC belongs to P. That imply either B belongs to P or C belongs to P. Suppose B belongs to P. Obviously ideal generated by B contain the P. By assumption P contain I, that means this is also contained in ideal generated by B. That imply always P equal to ideal generated by B. In other case, consider B not belongs to ideal generated P, but C belongs to P. That means C belongs to P means obviously this is the ideal generated by A, imply C equal to AD, where for some D belongs to the ring R. Since A equal to BC, just put the value here. Just put the value, then this would be BAD. Then A times 1 minus BD equal to 0. And since R is a PID, that means obviously R is integral domain. Therefore, from this line, since I have assumed A not equal to 0, that means obviously 1 minus BD equal to 0. And that implies from this line BD equal to 1. That means B is a unit. We all of us know, since I equal to ideal generated by B, and since B is a unit, that means this is equal to actually the whole ring R. Got I equal to whole ring R. That means our assumption is wrong. That means there exists no bigger ideal between the ideal P and the ring R. That means the ideal P obviously be maximal ideal. And this is possible only for the ring R is PID. As for example, if we consider ZX, obviously this ring is not PID, and ideal generated by 2 is a prime ideal which is non-zero, but not maximal ideal. We all of us know, because ideal generated by 2 contain in ideal generated by 2x, which is contained in obviously ZX. That means when a ring is not PID, then prime ideal does not necessarily this is the maximal ideal. But when a ring be PID, then prime ideal obviously would be maximal ideal. Today I will stop here. In my next video, I will discuss this topic elaborately, because this topic is very important for any competitive exam. And at first I will highly recommend you, please see my today's video with pay attention. See you soon, stay safe and stay positive always.